abundances of metal-poor stars and on stellar nucleosynthesis, especially the RNS processes for the heavy elements. And so she'll be telling us about all the work that she's been doing here for the last several years. And this is one of our last opportunities to hear from her. She'll be moving on to Texas A&M in a few weeks. So.
Thank you. And thank you all for coming today to hear about my work. As just says, I use metal-poor stars to explore the nucleosynthesis of the early universe. And I like to put up this version of the periodic table first because I think it emphasizes really well what I do, namely to use the absorption lines of the different elements in metal-poor stars to measure the abundances and then use that information to try and figure out how all these elements were created and how we actually formed this periodic table. But we actually do know pretty well how all of these elements were formed or the processes in which they formed. So starting from the beginning, this is going to be some repetition for most of you, but I like to sort of start with this to keep in mind how this works. So we have the Big Bang nucleosynthesis. It's just hydrogen, helium, not really much else. A little bit of lithium probably. And then we need the first stars to get more elements. So we form the first stars and we have hydrostatic burning and they explode. And in those processes, we form all the elements up to sort of the ion group and we enrich the interstellar medium in all of these elements. But all the heavy elements, so all the ones after zinc, all the ones down here, which you can't see, are produced in the two neutron-capture processes. So we have the slow neutron-capture process, which happens on a long time scale, basically. So you have a neutron capture, and then the element has time to decay before you capture another neutron. So you walk along this valley of stability, and then if you hit an unstable one, you go back to the stable one and sort of build up all the elements along this valley. So that gives us about half of the heavy elements after heavier than iron. So all the red ones down here are primarily S process elements. And then we have the R process, which I'm going to focus on today, the rapid neutron capture process, where you have a higher neutron flux, and it happens in a very short time scale. So basically, you go very far from stability and build up all the elements, and then at some point, the neutron flux stops, and you decay back to stability, and that then gives you all these blue ones down here. However, and we've known for a while that the S process happens in asymptotic giant stars, but the R process we haven't really been able to observationally pin down until last year, which you all know. However, the S process has a time delay in the AGB stars, so at very low metallicity, it's probably all some sort of R process that produces all of these elements. And as I said, we had last year this first observation of an actual R process event. We saw the neutron star merger, we saw the light curve with evidence of heavy element production. So quite soon after, the periodic table started to looking like this, where we thought we know all about in which environment all of these heavy elements were formed. But as I'm hoping to show to you today, this might be a little bit premature. We still have a lot of other contenders to where the R process might happen, and it's still sort of uncertain whether neutron star mergers can actually account for all the R process elements we have in the universe. So what exactly are these contenders? Well, yes, there are the neutron star mergers, and the models have shown that these can produce the elements that we need. So this is the mass number, and this is yield from the various different neutron star merger models, and compared to the solar system R process abundance pattern, which are these open circles. And as you can see, we can produce basically the entire mass range. We produce the second peak, the third peak. We also get some of the actinides. So it's all good. The models show us that neutron star merger can probably do this. But as recent as last week, we had a new contender on the market, which is the collapsers, where the Siegel et al. Paper showed that, well, these accretion disks can probably also do an R process, and which is shown over here, that they actually also, at 3 different stages during the accretion, they actually also get this neutron, or this R process abundance pattern, which compared to the sun. And these actually might be very efficient in producing these elements and might spit out up to 1 solar mass per event, whereas these spit out much less. But we also have other contenders. We have the fast rotating supernovae that have some jets where you can have an R process, which is shown in 15. Again, we have the solar system abundance pattern here, and then you have the different trajectories for different events of these supernova jets. Or it's debated whether these can actually get neutron rich enough, but certainly in the light end, we believe that these can actually contribute. And then there's the good old core collapse supernovae, which we now know is not neutron. The environments in the neutrino-driven wind will not be neutron rich enough to actually make a full R process, but we can probably still make some of the lighter elements sort of up to silver and palladium in these events. So suddenly we have 4 sites where we can produce R process elements. And none of these sites are very good at direct observations. We can't really have any direct observations of any of these sites to say, okay, this is the abundance pattern that this event spits out. So we need help from somewhere else. And this is where the metal-pore stars come in. And so just to remind you what metal-pore stars are and why they are really, really good to look for signatures of nucleosynthesis in the early universe, I have this slide. So metal-pore stars are basically just stars that have a metallicity of less than -1 Fe over H. And the evolution of the spectra you can see on this side, where we have down here, we have the sun, which is fairly metal rich. We have lots of line, lots of blending. And then we go to more and more metal-pore up here, where we have the one with absolutely no metals, so no lines. But as you see, the spectra get cleaner and cleaner, and we have fewer and fewer lines, basically. And what this corresponds to in interstellar medium composition is that, well, the sun is a signature of all the nucleosynthesis events that happen from the Big Bang and down to the time where the sun was formed. So it's a very combined, muddled up picture of all these events, and we can't really separate one event from another in the solar spectrum. But as we go to the more metal-pore stars, we start to probe fewer and fewer nucleosynthesis events, and down to here, where we've maybe only had a few or maybe even a single event. So the abundance pattern that we find in the metal-pore stars is essentially a clean signature of these nucleosynthesis events. So we can figure out what actually went on. And very luckily, we have a very small subset, of these metal-pore stars that are enhanced in the R process elements. So we can actually get R process element abundances from these stars. And this is shown here, or an example of the spectra is shown here, where you have the red star is one with low amount of neutron-capture elements, and the blue one, you have lots of neutron-capture elements. So you have, for instance, Europium over here, very prominent line. You get other neutron-capture element lines as well. And this group of stars we put into 2 categories. We have the mildly R process enhanced stars, the R1 stars, which has a Europium ion of 0.3 up to 1. And then we have the really strongly enhanced R2 stars, which have Europium ion of more than 1. And then we put in this barium to Europium ratio or condition to make sure that it's actually an R process, because all of these elements can be produced. I mean, all of the elements you see in this spectrum can be produced both in the R and the S process. But if we have more Europium than barium, then we know that it's an R process signature, basically. And that's what we want. So these stars are not new. The first one was discovered more than 20 years ago in this very famous CS 2282892052, which is, yeah, they all have lovely phone numbers. This one is actually not too bad. It gets worse. Yeah, so when people derive the abundances from this star, and you're going to see a lot of these plots that we have here. So we have the absolute abundances on the x-axis, we have the atomic number on the y-axis, y-axis and x-axis, and then we have the solar system R process abundance pattern, which is the solid line, and we have the solar system S process abundance pattern, which is the dashed line. And basically what people do is that since we have a very good idea about the S process, then they calculate what the S process produced in the sun, and then they subtract that from the solar abundances. So the R process abundances is basically just what's left over when you've removed the S process, which is a little bit tricky.
Scaled by the difference in metal elements.
Yes, obviously this is scaled to, well, usually we scale the star to the sun, so yeah, it's scaled, absolutely. But what you see is that for these heavy elements, this star's abundances is a very good match to the scaled solar system R process abundance pattern. It's a little bit more tricky over here with the light S process elements. But some years later, when they got even more data for this star, they did the same exercise. And you see that we actually have a very, very nice fit from barium to hafnium to the solar system R process abundance pattern. For the heavy elements, it's a bit more tricky, as I said, and for the lighter ones, we have a bit more scatter. But this beautiful pattern is something you're going to see a lot of today. So this is awesome. We can just go out, get a lot of these stars, and observe them and figure out what the R process is. And yeah, so I've mentioned now already something about the light R process elements, the heavy R process elements, and other things. So just to give you an idea about what this is the solar R process abundance pattern again, and then I've just highlighted the abundances, the element from which we can get abundances from ground spectra. These are the blue ones, so quite a lot. And then if we go to space, we can also get the red ones. And when I talk about light R process elements, we're over here. Usually we don't have any of these up here, so it's sort of strontium and up to silver. And then when I talk about the heavy ones, it's this middle region from barium to hafnium. Then we have the third peak, osmium, iridium. And then when I talk about the actinides, we're over here in thorium and uranium. And these two can actually only be produced in the R process. So if we have either thorium or uranium in the star, then we know an R process has happened. But before you get too excited and think, yes, we'll just find some R process enhanced stars, and then we'll measure all of these lovely elements, and then we can figure out the R process. It's a bit more complicated than that, because these lines are really, really hard, some of them. There are some easy lines like strontium, barium, europium. These have nice single unblended lines, very strong lines. And these elements we can get in most metal poor stars. This is fairly easy. But as soon as we go to some of the other elements, for instance, in the light end, palladium and silver, it gets really tricky. You can see the lines get blended. They get really weak. And also for the third peak element, like osmium and iridium over here. So to do some of this, we need really high resolution, really high signal-to-noise data. So it's really, really not easy. And then it gets even harder, and that's for the uranium, which is this little thingy here. And maybe, if you believe it, this little thingy here. This is currently the only uranium line that we have, that we know of in the spectra. I'm working with Alex to figure out if there are more that we can use, because it's this one. I mean, as soon as you have any kind of, there's a CN line right here, so if the star is carbon enhanced, then this completely disappears. Another one which is kind of tricky is lead, which is over here. And again, if you have any kind of carbon in the stars, then this line basically disappears. So to have any chance of getting uranium, we really need the highest resolution, highest signal noise, so resolution of 80,000 and signal noise of at least 100, if not more, in this very blue area. So this takes... sorry.
How long was the observation on the left?
Sorry?
How long was the observation on the left total?
This one?
Yeah.
So this one is a very bright star. It's a V of 10. And this was 6 hours, I think. This one is a V of 12, and this was, I think, 2 Magellan nights. Something like that. At least one. But this one is questionable. I mean, I think this one is I'm on this paper, but I think this is questionable. So yeah, it's give us time, please. Yes, but people have measured abundances in these stars. We're not completely at a loss here. Just not a lot. And this is what I'm showing here. So this is basically I think about 10 to 15 R2 stars that has the most abundance measurements in the literature. And as you can see, we have a few of them that has a pretty nice coverage, and then there are some that really don't have any kind of coverage at all. They have a few of the light, a few of the heavy, and absolutely nothing over here. But as you've probably noticed, all of these beautiful stars, again, this is a solar system R-process abundance pattern that we've scaled the abundance to, and all of these stars in this region from barium and up to sort of Hafnium-ish have a very, very nice match to the solar system abundance pattern, R-process abundance pattern. We have a bit more scatter over here in the light part, and we have a bit more scatter over here in the heavy end. It's probably easier to see if we collapse them all into one figure. Here you can clearly see that the light ones, well, strontium seems to scatter quite a bit. And some of these light ones that we don't really have that many abundances for also scatter. There may also be some scatter in this middle region, but I didn't plot the errors on this plot. And if I did that, then we wouldn't really believe that this scatter actually exists. There's something like that one, which is like, is that real or not? And then again, over here, with the third peak R-process elements and the thorium and uranium, we see quite a bit of scatter, which is actually real.
There is some correlation here, like the pink star, the pink Watson equals 2 star, is like it tends to be hot. If it's high in one place, it seems to be mostly high everywhere. So it does seem
This one.
Yeah, that guy. Or gal, or that point.
Yeah. So this is all normalized to an average over these. I think an average, or maybe no, I probably just normalized to europium. It looks like that's what I did. So of course the normalization also gives you some variation. But yes, it is possible that. I mean, it shouldn't be high everywhere because then it has slightly lower europium than it should have, I guess, or higher europium. I'm not.
Well, I guess the thrust of the question is like, is that possible? Is it possible to be enhanced? Is it possible? I mean, the model tracks here are correlated across atomic number. They must be because there's the same. So, is that an interesting thing, or is just you think?
Well, so that's what we want to find out, basically.
Okay.
We want to find out. I mean, so the scatter that we have in this end, we believe that's real, and the scatter that we have in this end, we also believe is real. But is it real that this star is consistently higher than the other ones in most of the other elements, or is that just an error thing? I mean, so these I've tried to take data from papers where they have a multiple number of stars, because otherwise a lot of this scatter is also due to different atmosphere modeling, different analysis probes, different line lists. It all goes in here and gives a scatter.
So it isn't the case that the scattering of points in a high atomic number is because of this problem of how weak some of these lines are?
Yeah, so, I mean...
You say it's real, so you...
Well, so I'll show you in a few plots why I think it's real. But yeah, some of the scatter is also because we have one line that we can use, and it's a hard line. Or maybe we have two, and there's... it's blended, and how well did people do that? But in this end, or at least thorium and uranium, there is actually a scatter. And that's what's shown in this plot. So it's quite a lot of things going on in this plot. But one of the reasons why we have a scatter in the actinides is because we have this class of actinide-boosted stars. And we may also have a class of actinide-deficient stars, which you can see in this plot. So this is the thorium to europium ratio. And some of them have... so basically, these stars are boosted in the actinides compared to the third or to the heavy R-process elements, which you could also see. Some of them are up here, so they have way more actinides than what you would expect from the solar R-process abundance pattern. And so when you have, these are plotted here as function of melicity, and then we have age measurements for these stars. And when you have a radioactive element, then you can assume something about the initial production ratios, and then you can calculate an age for these stars. And if you do that for these actinide-boosted stars, you get negative ages. It's not quite so good. If you do it for the deficient star, this is a star that Alex discovered in reticulum 2, you get ages that are slightly older than the universe. Also, not so good. Yeah, just slightly. So then there's this middle range where this technique actually works. But we have about 30% of the R2 stars which show this actinide boosted signature. And currently we have no explanation whatsoever for this. None of the nucleosynthesis models explain this signature. None of the three models I showed in the beginning that can do the heavy R process elements can actually do this.
So does this plot tell us that the idea of measuring the age of the universe from thorium, which I remember from years and years ago, is not going to tell us anything we don't know?
Well, so
It's from 3 to 12.
you have to be careful at least, because for these stars the initial production ratios we use are clearly not correct. There's clearly whereas I mean the ones where you follow the solar R process pattern all the way through, then it's probably a valid way of calculating ages.
When I first heard about this, though, I thought this was like a silver bullet that probably this thorium would be.
Yes. Yeah, but you have to be careful. Yeah. And we probably also need to look at the calculations that go into calculating the initial abundance ratios and figure out how.
Actinide boost rather than europium deficient? Is that, you know?
Yeah, well, so, I mean, so it's actinide boosted in terms of what you would expect from the solar system pattern. So they all match in this region, but then they have a lot more thorium and uranium out here. And they're all, I mean, yes, they have the similar europium abundances to the other R2 stars. It's R2 stars, all of them, so more than 1 dex enhancement in europium. Okay, so.
Does that just mean the scale should be stretched?
Sorry?
Does that just mean the scale should be stretched? The ages should be stretched to match the actual data, or do we think the 3 to 13 is the 0 to 13 is okay?
Do we think that? Sorry.
I mean, so the 0 to 13 points, we think we've calibrated those ages. We clearly don't think the ages that are negative or greater than are super real. Does that just mean the scale is wrong?
It
So
means that
it
means that our initial production ratios are probably not correct.
Okay.
And what's to say that they're correct for the ones that are in this area?
Yeah, exactly. That's what I mean.
Yeah.
Everything should be great calibrated.
Yeah.
The stretch is based on the half-life of thorium.
Yeah.
So well,
Okay.
so it can be shifted but not stretched.
Right. Yes. Okay, so that's the heavy end. We have a spread.
Stupid question, real quick. Does europium decay to thorium? Or?
No.
Okay.
Thorium is a lot heavier than europium.
Does the vice versa happen?
Uranium.
Okay, uranium decays to thorium.
Yes.
Okay.
Yeah. And if we could get uranium in these stars, it would be better because these two are sort of co-produced.
Exactly.
So that would be a more efficient age determination. But as I just showed you, the uranium is really, really hard. So good luck with that. So it would be nice if we could use this clock. But yeah, okay. So that's the heavy end. Then there's the light end, where, just to go back, I said that this spread is real. But there's actually also another thing that we need to consider when talking about light neutron-capture elements, and that is that we have this other class of stars that are not enhanced in the heavy neutron-capture elements, but are highly enhanced in the light neutron-capture elements. And this is sort of the prototype of those stars. So these stars don't have anything to do with the spread that I just showed you for the R2 stars, but they do have something to do with the general spread that there is in the neutron-capture elements when you go to, in the abundances of neutron-capture elements when you go to low metallicity. And so this star, as I said, is not enhanced in europium, but when compared to the solar, when you scale the solar R process abundance pattern to the europium, it has a huge amount of these light R process elements. And people have sort of looked at these stars and thought, well, then there has to be a process that produces much of this and not really a lot of this. And then there has to be another process which goes into the R2 star that produces not that much of this, but quite a lot of this. And Camilla Hansen looked into this some years ago, where she measured the abundances of silver and palladium in a large sample of metal-poor stars. These are not R-process enhanced stars, these are just regular metal-poor stars. And compared these abundances to barium and europium, which are some of the heavy R process elements. Barium is technically an S process element when you go to higher metallicity. And so what you see here is the silver over barium ratio and palladium over barium, silver over europium, and palladium over europium as function of barium and as function of europium. And if these elements, if silver and barium and palladium and barium were co-produced, you would see flat trends in these plots. But as you see a clear anti-correlation, then it highly suggests that there's two processes, one that's responsible for the silver and palladium, and one that's responsible for the barium. And similar down here with the europium, it doesn't seem like whatever produces the europium produces silver and palladium. It doesn't mean, I mean, you can have some co-production, but there seems to be, there needs to be an additional source of these elements that is not, that doesn't produce this one and vice versa. Well, that doesn't produce as much of this one and vice versa, basically. So people are fairly agreeable, or people in the stellar community sort of agree that we have something that produces light elements, and we have something light neutron-capture elements, and we have something that produces heavy neutron-capture elements. But what exactly this is this a variety of neutron star mergers? Is it core collapse supernovae? Is it the jet supernova that is responsible for this signature? We don't really know. So we need more data. And then more recently, Ian Roeder looked at the light neutron-capture element signature in R process enhanced stars. And so what he found is that they actually have a fairly consistent pattern in this area. So what you see here is the absolute abundances of the R process of the R1 and R2 stars subtracted with the solar. So if they match the solar, they would be all on this red line in each of the plots. And then it's for different levels of R process enhancement. So we start at, probably can't read this, roughly 0.5 europium of iron, and then all the way up to 1.7-ish europium of iron. And what you see is there's actually quite a consistent pattern. So yttrium, for instance, is low in all of them. And we have this downward trend, which sort of seems to be consistent all the way down. So these are, so it seems that within the class of R process enhanced stars, there is some similarity in the light neutron-capture elements. But again, we don't really know what causes it. Yes, and then there's the final sort of evidence that neutron star mergers probably are not the sole candidate, is that we basically see strontium and barium in every single metal poor star where we've been able to measure it. And this is what Ian Roeder alluded to in 2013, where he took all the literature data he had on, there was on strontium abundances and barium abundances, and then he calculated, well, what is the detection threshold in a 4500 Kelvin star, and does any of the upper limits that we have in any of these stars, are they consistent with there not being any strontium or barium in the interstellar medium from which the star is formed? And it doesn't. I mean, all of the upper limits, none of the upper limits exclude that there could have been strontium or barium in the interstellar medium. So it seems like we have something that very, very early on puts both strontium and barium into the interstellar medium. And here the neutron star mergers kind of have a problem with the delay time of those. So some kind of supernova seems to be a better suggestion for these.
Did he have a time scale that he argued for from this analysis?
No, he didn't. I mean, this is 5 years ago, so it's before we. I think he just.
This was a purely observational point.
Yeah. Just saying that. I mean, none of these upper limits. I mean, the detection. None of these upper limits says that there is no strontium or barium. We don't have a star with a low enough upper limit on strontium or barium to say that there is no strontium or barium in the cloud from which it formed. It could still be out there. I'm not saying it's not, but.
I was more curious whether this would argue that you have to make it within 10 million years or 100 million years.
Well, you have to make it at the same time scales that you make -4 stars, basically. So all of this I showed you so far has been in for stars in the Milky Way halo. But as you've probably also already know, we also find R-process-enhanced stars in dwarf galaxies, and we have this famous Reticulum 2 that Alex discovered a couple of years ago, which is an ultra-faint dwarf galaxy where 7 out of the 9 stars analyzed showed a strong enhancement in R-process elements. So finally, we actually had an environment where we knew that an R-process nucleosynthesis event had happened. But this is actually not the only ultra-faint dwarf galaxy with R-process-enhanced stars. We also last year discovered Tucana 3, which show a mild enhancement in R-process elements. So these are all R1 stars. And this is the brightest star in that galaxy that I analyzed. And just to show some of the neutron-capture lines that I measured in the star, Europium, of course, but also some of the more difficult ones. And when comparing the abundance pattern of this star to the solar system R-process abundance pattern, we have again the very nice match. And in the light end, a bit more uncertainty. These stars are, of course, somewhat fainter, and the abundance analysis is somewhat harder, so the error bars on this is also larger. But we went after more stars in the galaxy, and I've analyzed 4 more of these stars. This is the star I just showed you. And it turns out that all of these stars have a europium abundance of roughly 0.5, and all of them have R-process abundance patterns that match the solar system R-process abundance pattern. So the dashed line here is the solar system S-process abundance pattern, which is clearly not a very good match to our data. Tucana 3, so you might question why we have Reticulum 2, which has this extreme enhancement in R-process element, all of those for our 2 stars, and why we then have a similar galaxy which has only R1 stars, basically, so a lower enhancement. But Tucana 3 is in the process of being stripped, so it could have been more massive in the past. It's also possible that we had an event that just didn't spit out as much R-process material. It's slightly uncertain. It's really hard. It's hard to pinpoint and say this is what happened. But we have another environment where we know an R-process event has happened. And this got me thinking, well, what about all the classical dwarfs that we have around us where people have looked at stars in high resolution? And do they have R-process-enhanced stars? And yes, they do. We have, so Minor has quite a few. Draco has quite a few. Fornax has also quite a few. And if you plot all of their abundance patterns, we have the same beautiful match. And so again, this is the star in Tucana 3, and then the other ones are stars in classical dwarf galaxies, where they had more than 2 measurements. A lot of them just have barium and europium, but where they have more than 2 measurements. And you may say that the scatter is larger here, but it's a data quality issue. Again, if the error bars were on this plot, you would it would erase this. Well, it wouldn't erase the scatter, but it would make the scatter insignificant. So clearly, we have an R-process that produces this very consistent abundance pattern in the heavy element region, irrespective of what environment that it's in. And the distinction between the highly R-process enhanced and the mildly R-process enhanced is probably just a dilution feature, or because the event didn't spit out as much material, but it still spit out this very beautiful pattern. Yes, but we still have the problem in the light end, and in the heavy end, I think there's one in Ursa Minor that has a actinide abundance, but otherwise none of the dwarfs really do. So the question is, now I've shown you all sorts of abundance evidence that we have, but I haven't actually said, so this is evidence that we have a neutron star merger, or this is evidence that we have a core collapse supernova or something. So what do we need to learn more? What do we need to get further in this field? And as a stellar spectroscopist, I say we need more stars. So when I started at Carnegie, about 30 R2 stars were known. A few more R1 stars. But with 30 stars, it's really hard to say anything significant. The statistics is not very good. So we need more R-process enhanced stars. Another thing is, so I showed you the plot with all the abundances of the R2 stars that had decent measurements in the literature. and that was about 15 stars. And only about half of those actually had a full abundance pattern. So we need a brighter sample, because the current sample that we have is basically too faint. It will take too much telescope time to get the entire R-process abundance pattern from these. So we need a brighter sample, and then so far it's been, people have discovered an R-process enhanced star and an R2 star. They've done the abundance analysis, they put out the paper, then another group discovers another one, they put out a paper. And so it's very inconsistent, the whole analysis of these stars. So we need someone to take a whole bunch of these stars and analyze them in a homogeneous manner, so we know that the scatter that we see is not due to different ways of determining the temperature of the stars, the gravity of the stars, different line lists, all sorts of things that go into the analysis. And in comes the R-process alliance. This is basically what we're trying to do. This is a collaboration that started just over a year ago. And our main goal is to identify 100 new R2 stars, and then derive this detailed abundance pattern for these stars, and then collaborate with people who know a lot about nucleosynthesis, and people who know a lot about galactic chemical evolution, and try and see if we can solve this R-process issue. So we select stars from large spectroscopic surveys that are bright, so we can observe a lot of them in a short time, and we know that we actually can get decent spectra. And then we choose them to be cold, so that we know we can get a European abundance, or at least an upper limit. And we choose them to be metal poor, so that we know that they have only seen a few nucleosynthesis events. And then our abundance criteria for labeling these stars is, of course, the R2 label that I told you about earlier, and the R1. But then we also defined a label which is called the limited R stars. And these are the ones that have large enhancement in the light neutron-capture elements, but not exactly in the heavy ones. So with this class, we hope to probe this light R-process that we know is there, but we don't really know that much about. So we hope to learn more about it from these limited R stars. And then we take our sample, and people, well, I should thank the Carnegie TAC for giving me a whole lot of time on this lovely telescope to take my sample there and look for these stars. So I've spent many, many nights with the shell spectrograph from the DuPont, taking reasonably high resolution spectra of these stars and high signal to noise to look for the European line in these spectra. And we need this resolution to do this. We can't do it with any kind of lower resolution spectra. And these are sample spectra, so we have a normal metal poor star with no R-process enhancement, and then we have a strongly R-process enhanced stars. And as you see, we have the beautiful European line, which is what we're looking for. But actually also this dysprosium line has turned out to be a very good telltale of whether the star is strongly R-process enhanced. So it's fairly easy for us to pick out these stars from the data. And we've analyzed, this year, we've published the first data released from the Southern Hemisphere. And we found 10 new R2 stars. So what you see over here is a histogram of the number of new stars we found in the different categories. It's function of metallicity. The blue line here is the R2 stars. Actually, there's 12 in here because we had 2 rediscoveries. A number of R1 stars, I don't even remember how many, and quite a number of our limited R stars as well. And what you see is that we actually discover the R2 stars over our entire metallicity range. So up until this survey, most of the R2 stars had been found down here, but we find them at more metal-rich end as well. And well, the R1 stars are also all over the place, whereas the limited R stars, this red curve, seems to have a preference for the lower metallicity, which is interesting, and we need to look into that. And just to show you how good we are in terms of brightness, over here we have the literature R2 stars that were discovered before this survey, which is the green dashed line here. You see they're all pretty faint, and then we have all of our really lovely bright stars here. So we can do a lot of stuff with these R2 stars that we've discovered because they're so lovely and bright. And just to show you some abundances that we measured for these stars, we have the europium over iron, which is the discriminator whether they are R1 or R2 stars. You see the green ones here are the R1 stars, and the blue ones up here are the R2 stars, and then we have the limited R stars down here. And then we have a comparison sample behind just to see that we actually sort of find the same range of europium abundances as has been found before. And we also see that when you go to lower metallicity, you find a larger spread, which is also seen in the literature abundances. And then we have the strontium to barium ratio, which is the discriminator for the limited R stars over here. And actually, as a function of europium, it actually seems to be a pretty good separator, at least between the limited R and the R2 stars. We have a few up here that could be interesting. But it seems like the strontium to barium ratios decreases as you go to higher and higher europium, sort of emphasizing or supporting the notion that the R process that created the elements in these stars might not be the same as the R process that created the abundances in these stars. Yes?
So you kind of answered a little bit, but should I think of like R1 versus R2 as being physically distinct?
No. I probably shouldn't say too much about that, because, I mean, I think the R1 and R2, it's a dilution issue. It seems to be the same R process, as I've shown. I mean, all the R1 and R2 stars, they follow the same pattern in this heavy R process region. So whether you are here or here in your europium enhancement seems to be either how much the events spit out or a dilution thing. And I think mostly a dilution thing. But again, I mean, we need to look at larger samples to be sure, but yeah. But the limited R stars are definitely something different, which we hope to probe. So this is basically the status of the southern search. We have observed about 570 stars, and 200 of those have been analyzed. Now, the first sample that came out this year, my paper, where we found 10 new R2 stars, that was a very, very good sample. In the next 100 stars, we've only discovered 2 new. But that puts the fractions down to what we actually expected before we started the survey. We expected to find about 3% of these stars to be strongly R process enhanced. So this number is not completely off. And the R1 stars, they sort of just follow in great numbers. And also the limited R stars. Nobody's actually looked at these limited R stars, or at least not with this definition before. So so we don't really know how this number compares to the literature that very well. And so we have 370 stars that we haven't looked at yet, but from just looking at the spectra at the telescope, we probably will find another 20 R2 stars in this, which means that we, just with the data we have now in the southern hemisphere, we should have doubled the sample of R2 stars. But if we just talk about the ones we've actually identified, then this is also, we also have efforts in the north. And if we combine all of our confirmed identified R2 stars, then we have 19 of those, which means we have an increase of the sample of about 60%. So I'd say that's pretty good. And let me just use my last minute showing you some highlights from the Rpa survey, or the Rpa work. So this was the first R2 star that we discovered. It was actually discovered before we were organized and called ourselves the R process alliance. But what is great about this star is we have a uranium abundance, and this is only the 4th star that has ever had uranium discovered. So that's pretty cool. It's not an actinide boost star, but that's also okay. And otherwise, it's the same signatures that you've seen in multiple plots already today. So I'm not going into too much detail about that. It's not particularly bright, but it had uranium, so yay. Then there's this one, which Charlie Sakari discovered in the northern part of the survey. And at the time, when she published the paper, this was the brightest R2 star that we'd found. It was also one of the most metal-rich ones. We have one at minus 1.5 in the southern sample that we need to look at, but this was pretty metal-rich. And what Charlie showed is that when compared to this guy here, CS31082, which is one of the first R2 stars to be discovered, and which is a -3 star, I think, that even over this metallicity range, we still have this very perfect match to the solar system R process abundance pattern. But it wasn't long before we had a new R2 star that was even brighter. And this is Erika Holmbeck, who was visiting last week, who discovered this one at the in the data that we're taking with the Madonna Observatory. And this star is actually really interesting because this is the most actinide-boosted star that has ever been discovered. So this was in that age plot I showed you, the one very far up, giving a very negative age. And Erika is working on figuring out what the nucleosynthesis behind this is. And then, I think only a couple of weeks ago, we've had this star published from Ian Roeder, which is now the record holder for the brightest R2 star and also the most metal-rich R2 star. And again, we have this beautiful match. Unfortunately, no uranium in this star, but we have a thorium abundance. So we have quite a few interesting stars, and hopefully when I get time to look at the DuPont data in more detail, I'll find some other interesting stars as well. And as I said in the beginning, one of the whole points about this collaboration and this exercise is actually to do a homogeneous abundance analysis of these stars. So these 4 stars has been analyzed in roughly the same way, at least with the same line lists. And this is all of their abundances put together. And well, the question is this spread real? Maybe.
So the 3 different methods of different colors.
Sorry? The different stars. These are the 4 stars that I just showed you. These 4 R2 stars that we've discovered. So this is just...
Lots of different people doing it to see what...
Well, so these are from different people doing it.
Okay, so well, but it's a different star.
So it's still not as homogeneous as I would like it to be. But at least we have the same approach for determining stellar parameters. We have the same approach for doing the actual abundance analysis. We use the same line lists, all that sort of thing. So this is probably, I mean, so some of the spread that we see here in this element, here we have consistently lower than the R-process abundance pattern. Those are some of the things that we need to look into now and see, is this really real? But it could be real just from looking at this data. But otherwise, I mean, we have remarkable agreement on some of the other elements. And then again, even with our very bright, very high resolution, very high signal noise sample, we still don't have very good coverage up here. So this is still really, really, really hard. We have pretty good coverage on the 3rd peak, and we also have pretty good coverage for the thorium. Again, uranium is really hard. Lead is also really hard. So we need more stars, brighter stars, better stars, basically. So I will leave you with my summary and take more questions if you have. Yes?
I think I have one fast one and one maybe a little harder one. One thing that I noticed is that, what's it, ytterbium, Y?
Mm-hmm.
That seems to be low
No,
on, like,
Y is uranium.
What
Sorry, ytterbium is, yeah.
Ytterbium, right?
Yttrium.
Okay, sorry.
Yes.
Big whiz. I work at like R16.
This one.
So, yeah, that one.
This one.
It's low a lot.
Yes.
Is there a weird, what's up with that? Okay.
Your answer is as good as mine.
And this
I don't think anybody's actually looked into that. But yes, it's consistent. Maybe Andy has a better answer to that. No, okay.
Is that
On that
down?
point, so you call them limited R or something? What do you call them? Sorry, I get
Well, the ones that are enhanced in the light ones, I call those limited R stars. Yes,
okay.
but these are all R2 stars. So
I think you're prejudicing yourself there because unless you know it's an R process, you should be
yeah, R. Yes, no, that's another thing. We don't actually. I mean, there are.
Tony will know about it. There's a thing years ago it was called the alpha-rich freeze-out type 2s and
Right.
neutrino-driven and those had alpha particles and neutrons
Yes,
pushing up
yes.
the strontium.
Yeah.
So you could make those maybe that way. But I don't
Yeah.
know if
I mean, so the
same entropy problem with the R process is also a problem for that, but that was one way that those elements were predicted at some time, and that wasn't really R.
yeah, I mean, the labeling of calling it an R process is in the lack of a better word, I think.
Neutron-capture.
Yes. I didn't pick the limited R. I picked the limited, but not the R. But yeah, and also, I mean, we have other contenders at low metallicity that can do neutron-capture elements. We have the spin stars that can do some sort of S process. We have a range of supernovae that may also be able to do some S process in the explosion. I mean, there's a whole bunch of stuff down there that we don't really know that much about. So it would be really good to get a large group of stars, both R process enhanced and non-R process enhanced. I mean, just normal metal-poor stars, and get some of all of these elements and see what we can figure out what's going on in this end. Sorry, I think Louis had another.
The last one is: does anything in the dwarfs that you analyze correlate with their star formation histories? We have star formation histories from resolved CMDs for some of those, and I don't know if there's been.
So I haven't looked at, but that's a great thing about. That's why we want to find them in dwarf galaxies, so we can do something with the environment and figure out if I mean, did we have an initial mass function that could end up in the neutron star merger, or could we have a collapse, or what could we have? So yeah. Yes.
So as you go through, you argue that there's more dispersion in different regions, and maybe that means there's more than one source. Has anyone gone through, maybe there's just not enough data at this point, but then some sort of principal component analysis and just said, hey, these ones are always correlated.
No, not yet.
Okay.
But yes, it's something.
Or how many components would you need? For example, could 2 components explain all this data, or would you need 3?
Yeah. Because I mean, one thing is multiple sources, but it could also just be one source that varies in the output. I mean, that's also.
And then the other question, I guess, is: do you feel like on the nuclear side you have enough information to do comparison to models, or is that still lacking?
I think that's still lacking. I'm not an expert on models, but so far it seems that they can do quite a lot within the models. And I'm not. I mean, so I'm not sure.
Wiggle room, right? You have the neutron fraction, the YE, you have the entropy, you have the speed of the material. All of this.
Yeah. Well, I mean, so what most of the models do. Sorry.
It's only a continuum in each of those parameters.
But like YE, for example, you get very distinct patterns if it's like YE above like 0.3 or under 0.3, and it's like nothing else.
So what most of the models do is that they compare to this star that I showed at the very beginning, this CS, the very first R2 star that was discovered. That one. And they just say, okay, we can match this one, so we're good. So we need to throw some more data at them and say, no, you need to match this as well and this as well, I think. Ian.
So you talked a bit about the systematics. Do you have a plan for the 4 groups to share their spectra?
Well, so all of these spectra or all of these stars that are shown at the end, we're all part of the opposite line, so we all have each other's spectra and we can all do the analysis and everything. Not. Well, there's a plan to.
You have to do that.
Yes. Yeah, to figure out whether these wiggles are actually real. So there's a plan to, within our collaboration, to homogenize the process and make sure we all do it in the same way. So then there's the personal sort of influence on the analysis. But basically, the plan is that.
What do you think is the major personal equation? Is it measuring the line strength? Is it placing the continuum? That's what Christine needs.
That's one of them, probably. It shouldn't be that much of an issue because these are really high-resolution spectra or high signal-noise spectra, so the continuum placement should be easier. But
some of those lines, for instance, are scattered is because they're in regions where there's no continuum. Far on the other side.
Yeah, that's true. I mean, these are also cold stars, most of them. So, I mean, you have lots and lots of lines, and it gets hard. I'm not sure so I haven't actually, I don't think any of us within the collaboration has sat down and said, okay, I'm going to analyze this star, and you're going to analyze this star, and then we're going to compare and see what we find with the same tools, and then we're going to compare and see if we find consistent numbers. But so I'm not entirely sure what the. Yes, it would be.
It doesn't sound like there's enough of a standard to say this method is best in essence. Wouldn't you be better just carrying these different methods along so you have some sense of the scatter that can be introduced just by the difference in the way you treat the spectrum and measure things? Instead of coming up with one, okay, this is where we're going to do all the stars based on putting all these three methods together. So.
Well, so in principle, the method that's been used for the 4 stars that I showed at the end are the same. So it's on a person-by-person level that because I mean the line list is the same, the way we determine parameters is the same. So.
Setting the continuum, how you do that has to be one of those things that each code maybe does a little different.
Well, or each personal vision when you look at because we do synthesis and you look at, I mean, you look at the lines and you say, okay, I think the continuum is here, and somebody may put it a little bit higher or a little bit lower. That's, I mean, it should be standardized, but it's not.
But it
Feeling
doesn't need
better,
to
we
be
have the same
standardized.
problem in quasar spectroscopy.
Yes, true.
I think I'm arguing that you don't standardize it if you really can't tell. That it's better to have several people doing it, setting a continuum.
It depends on what question you're trying to answer. If you're trying to determine the scatter of one element, then you should have one person analyze all the data in exactly the same way.
Yes.
From star to star, you're saying?
Yeah.
That's true.
Yes.
But if you're trying to compare the whole sequence of measurements, then that's something. I'd take that.
True.
So on the next slide are the elements that show possible scatter. We talked about yttrium, and I think there's like number 70 or whatever that is.
Yeah, and I think that was 71, isn't it? I think that's the lutetium.
Is there a reason to be particularly suspicious of those because of blending or?
Yeah. Yes.
So it's completely consistent with there being no variation in any of the spectra except.
Well, I mean, that's the question. The question is if this is because of blending and the difficulty of deriving these abundances, or if it's actually a scatter.
I mean, the quick thing you could do is just overplot the spectra on top of each other if they look different the first place.
Yeah, but I mean, these 4 stars all have fairly different temperatures and parameters, and I mean, this is scaled, so the actual abundances of the star vary quite a bit. Yes.
Does chemistry or other astrophysics ever matter, like diffusion or something at the low mass or high mass, and you never take this into account in the models?
I'm not sure.
Uranium isotopes with mechanical centrifuge, so there could be some other process, that changes the uranium abundance or the abundance at the very light.
Yeah, no, we don't.
Like if multiple generations of stars, you could have dust taking out some things.
Yeah. So these are all subgiants, or most of them are subgiants. Some of them are dwarfs. So we don't really believe there to be any alteration of the abundances from the interstellar medium for which they're formed. So, anything else, Andy?
I think your statistics, you should really emphasize those and publish those, because I think that's a critical way of figuring out what these sources are that are making these different groups of elements. Back in the day, I mean, I remember we had 40 times the solar uranium to iron ratio, so it could be more than 1/40th of the total population. So arguments like that might help you. It would be really good to have statistics.
Yes. Yes.
So that other people with their models then
Have to explain the yes.
The question I had was these recent R2 stars, particularly the bright ones. Have we looked at their kinematics to see whether there's any whether they're related or their angular momentum vectors are all pointing?
Yeah. So Ian just published a paper where he did the kinematics for my southern sample. Alex, do you remember that? I don't.
So not all of them, but some significant fraction of them have negative or retrograde. But beyond that, nothing. They're not actually like necessarily.
You don't see pairs or anything.
So I think he picked out pairs, but yeah.
But he did, yeah.
So those are
Well, so that's a
So they could be, yes. 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 Well, they're clearly all Hansen dwarf galaxies, right? Because they're my stars. So, okay.